Welcome to Lesson D, Simplified Radical Form. Does that feel like deja vu? Does that feel like deja vu? Yeah, we were just playing with simplified radical form in Lesson C, right? Except in Lesson C, we were doing square roots, and in this time, we're going to be doing higher roots, things like cube roots. So here's what a square root radical looks like. We saw that in the last lesson. Well, if you want to take a cube root, you put a little 3 on the shelf, and if you want to take a 4th root, you put a little 4 on the shelf, and if you want to take a 5th root, you put a little 5 on the shelf, and so on. So it's, like I say, it's like we're just kind of adding another dimension to our rooting procedures or whatever. But let's start over here with what's familiar, because I actually ripped this off from the last lesson. There's a distinction I want to make between what this symbol means and what it means to take a square root. They're not exactly the same. Very close, of course, but not exactly the same. This symbol, remember, stands for principal square root. And the principal square root is always the positive root. So 9 has 2 square roots, right? Plus 3 and minus 3. But the radical 9 is just the positive 3. So the radical symbol always gives you a positive result. Well, in case of square roots anyway, it always gives you a positive root. The principal square root is always positive, is what I should say. The principal square root is always positive. Coming back up to here, if you were solving this equation, you'd say, oh, something times itself is 9. Isn't that what square roots are? Something times itself. Yeah, that's what square roots are. So we could actually write the solution this way, but remember again, we have to put that plus or minus in front. Because this symbol here, radical 9, is just a 3, just the positive 3. So you have to yourself, write the plus or minus in front to make sure that you're getting both solutions to that equation. So this equation has 2 solutions. X squared equals 9 has 2 solutions, both a plus 3 and a minus 3. 9 has 2 square roots, is another way of saying the same thing. Okay, so that's kind of old. Now this is kind of new, this cube root thing. So this symbol here means, guess what? The principal cube root. Now, I'm not going to say that the principal cube root is always positive, because it isn't always positive. First of all, what is the cube root of 27? Think to yourself, what times itself, again, is going to give you 27? Well, you could just kind of, start with little numbers and say, well, I don't know, does 1 times 1 times 1 work? No way. How about if I did like 2 times 2 times 2? Does that equal 27? No way. What if I did 3 times 3 times 3? Would that equal 27? And the answer is yes. 3 times 3 is 9. Times 3 again is 27. So it turns out that the principal cube root of 27 is 3. And it's positive, but it's 3. Now, compare that up here. If you wanted to solve for x here, okay, the question is, what times itself 3 times gives me 27? And we know that's one of our answers, is 3. That's one of our answers. But that's only the principal cube root. There's 2 other answers. There are 2 other answers. X could be equal to 3, and it could also be equal to, let's see if I get this right. I'm going on memory, which is always dangerous, but I think it's something like negative 3 plus or minus 3i. Square roots of 3, that whole thing over 2. That counts as 2 more roots. Negative 3 plus 3i roots of 3 divided by 2 is 1 root. Negative 3 minus 3i square roots of 3 all over 2 is another root. Now, I'm not going to show you how to find those yet, not until at least week 4. But the point I want to make here really, and we can just kind of put that in parentheses and say, whoa. Or that's not how you say whoa, that's how you say yikes. Whoa, whoa, nifty, that's what I'll say. But the point I want to make is that there are 3 solutions to this equation. X to the cubed equals 27 has 3 solutions. Another way of saying the same thing, 27 has 3 cube roots. Every number has 3 cube roots. So remember back here we were saying, yeah, every number has 2 square roots, and you were like, yeah, I knew that. Every number has 2 square roots. Well, this is cool. Every number has 3 cube roots. 3 cube roots. So when you're solving an equation like this, one of the things we're going to have to figure out is how to find all three solutions. And again, that's in the future a little bit. One of the solutions you can kind of see. You can kind of say, oh, 3 is one of them, because 3 times 3 times 3 is 27. But there's going to be 3 cube roots. Anyway, coming back down to this, when you see this radical symbol, it means, oh, don't worry about those. We don't care about those. We just want the principal cube root. So it's actually making our life easier, isn't it? It's like, oh, it's the 3. Yeah, the 3. Yeah, that's the principal cube root. Okay, now. Fourth roots. Hey, you want to guess? How many fourth roots does 81 have? First of all, what's a fourth root? A fourth root means you have to multiply something times itself again, times itself again to get 81. So the square root of 81 is 9, but the fourth root of 81, well, again, the best way to see it at first is to just kind of ask yourself, well, I know 1's not going to work. 1 times 1 times, no. And I know 2's not going to work. No. 3 times 3 times 3 times 3, what's that? 3 times 3 is 9. 27 times 3 again. It actually turns out to be 81. 3 is the principal fourth root of 81. So that's, again, what this symbol means is the principal fourth root, which is 3 again. Okay. This equation, by the way, has 4 solutions. This equation up here has 4 solutions. What are they, for heaven's sakes? Well, you know that 3 is one of them. 3 is one of them. Negative 3 also works, because if you go negative 3 times negative 3, you get positive 9. Times negative 3 times negative 3 again, it's going to come out to positive 81. So those are 2 of your roots. And it turns out there's 2 other roots, which are not too hard to find. 3i and negative 3i. And it occurs to me, maybe you haven't seen I before. Well, if you haven't seen I before, kind of don't worry about it for today. But I is, it's basically, well, it's basically, you can think of it as the square root of, the principal square root of negative 1. So, yeah, it's mysterious. Don't worry about that right now. It gives us a way to write solutions that we couldn't otherwise find. Let's put it that way. So 3 is one solution, negative 3 is one solution, 3i is another solution, negative 3i is another solution, okay? But the principal root is this one. That's the principal root, okay? It's what do you want to call it? The obvious root? The good root? The nice root? I don't know what you want to call it. And just to finish the pattern here, this would mean the principal fifth root of 32. Now coming back up, if you were solving an equation like this, you would be thinking in your mind, I need to find fifth roots of negative 32. And what you got to keep in mind is there's 5 of them. Well, let's put it this way. There are 5 fifth roots of a negative 32. The principal of those roots is, well, again, just ask yourself, what would it work if could I use 2? 2 times 2 times 2 times 2 times 2. It does come out to 32. Now, if you use a negative 2 times itself, times itself, times itself, times itself, times itself, you will get negative 32. And therefore, the principal root is negative 2. The principal root is negative 2. I should actually be writing that down here. So the principal root is 32. The principal root of negative 32 is negative 2. Now, if I wanted to solve an equation like this one, where the question really is find all of the fifth roots of negative 32, there would be 5 of them. There are 5 fifth roots. 4 are complex. And by the way, complex, that's what these things are. When you go sticking i's in there, the letter I, the number I should say. When you put the number I in, those are called complex solutions. So 4 of those fifth roots are complex, and it's beyond our ability to find them right now. But for today, we can find the principal fifth root, and that's all that this radical symbol means, is the principal square root, principal fifth root. So we're in good shape in that sense. Now, what I need to mention here is Remember when we did this kind of thing, we said the problem is you can't really just say that the square root takes a square off, because it doesn't always work that way. It would work if x was a positive number. If x were a positive number, something like a 2, right? You could put a 2 in there and square it. And then when you square it, it's a 4. When you take radical 4, you get 2. And so it works. If x is positive, it works fine. But what if x is negative? Well, if you take a negative 2 and square it, you'll get a 4. And then the principal root of 4 is also 2. But notice this is not x. X was negative 2, remember? We used x equals negative 2, and what we're getting here is not negative 2. In other words, we're not getting the same thing here and here. Here it's a negative 2, here it's a positive 2. It's a mismatch. So remember how we dealt with that. We said, well, in general, what we could do is we could say it's the absolute value of x. And that's just to make sure that the right side of the equation is always positive. This side of the equation is always positive because this symbol means the principal or positive square root. It has to be positive. If I go and put this in absolute value bars, I can make sure that both sides of my equation are positive. And you can, I'll demonstrate that this is working just fine. Let's say x was a negative 2. Well, if I squared it, I'd get a 4, and the principal square root of 4 is 2. So I'm supposed to get a 2. Well, what would happen if I put a negative 2 in here? Because x is negative 2. If I put the negative 2 in here, well, I'm going to strip the sign off, and it's going to be a 2. So the equation will be valid. So to make sure that the equation is actually valid, it's a good idea to put these absolute value bars on here. Now, I need to point out that's true for all even roots. The principal root should always come out positive. Okay, so if x were, let's see, that was 81, right? If x were a negative 81 here, wait a minute, that's not what I want to say. How would this work? If x were a negative 3, yeah, that's it. If x were a negative 3, and I took it to the 4th power, it would become a positive 81. And when you take the principal 4th root of positive 81, you get positive 3. And the only way to make a positive 3 over here is if you put the negative 3 inside of absolute value bars. So it turns out for all even roots, circle that sucker. I'm going to say often, because it's not always necessary, but often necessary for even root radicals. Where you going? For even root radicals. Okay. It's not necessary for odd root radicals. And why not? Well, the cube root of 27, well, let's put it this way. The cube root of x cubed really is x. And it doesn't matter if x is positive or negative. If x is 3, let's say, x was positive 3, you'd have 3 cubed is 27, and the principal cube root of 27 is 3. It works. What if x is negative 3? If x is negative 3, and I cube it, I'm looking at the cube root of negative 27, and the principal cube root of negative 27 is negative 3. And so the negative 3 that I plugged in here is coming out over here the same. So for odd roots, it doesn't matter. Odd roots, we don't have to worry about any of this stuff. So that's kind of nice, right? So I'm going to just make a little symbol here. No worries for odd roots, odd root radicals. And then I can say ditto over here because 5th root radical was an odd root radical. So that absolute value thing that we were doing in the last lecture for square roots, well, you always have to worry about that when you're taking square root radicals. Turns out you always have to worry about that when you do any even root, a 4th root, a 6th root, an 8th root, anything like that. You need to worry about whether the right side is coming out positive. For odd roots, life is a little less stressy because it doesn't matter. No worries. The principal 5th root of negative 32 is negative 2, right? You don't have to, it's not going to always come out positive, in other words. go away. It's not going to always come out positive, in other words. The cube root of -8, for example, what's that? Well, it's -2. The principal cube root of -8 is -2, because -2 times -2 times -2 again is -8. So it's not the case that you always get a positive answer when you're playing with these odd roots. You could get plus, you could get minus. Not the case with these. Even roots, you have to get a positive answer. Okay, so that's kind of like the theory behind these radical symbols that we're going to be using. Okay, so just again, it's always a good idea once you've gone through something is just kind of, before you keep trudging on, just stop for a minute and say, well, what just happened? So what just happened was, one thing we said was, hey man. We said, hey man, we did. We said, hey man, 9 has 2 square roots. Every number, in fact, has 2 square roots. Every number has 3 cube roots. Every number has 4 fourth roots. Every number has 5 fifth roots. Okay, so if you're solving an equation of these forms here, where like the problem is, find 2 numbers that multiply to 9, in other words, you're finding the square roots. Find a number that when you multiply by itself 3 times, you get 27, which is another way of saying find cube roots. But you want to find all cube roots if you're solving this equation. These symbols mean the principal roots, which is kind of like the first root. In the case of even root radicals, it's going to be positive always. So in case of even root radicals, you got to worry about these absolute value bars. You got to make sure that the right side is positive. You can't have the right side be negative, or else you have a false equation. That's a no good. Whereas for odd root radicals, you don't have to worry about any of that stuff, because every now and then, you take a cube root of a negative number, you get a negative number. It's not the case that the right side's always supposed to be positive. It's not the case at all. So don't worry about the odd roots. So what we got to get to now. Now comes the main, what do you want to call it? Practical work, I guess, of working with these radical symbols. Yeah, I think it's time we did it. So the rest of this is going to follow more or less the same sequence as the previous lesson. So if you're pretty good on the previous lesson, this should seem almost natural. One of the things we did when we were simplifying square root radicals, we were hunting for perfect squares, right? I said, hey, if you can find a factor of 4 or a factor of 9 or a factor of 26 or a factor of 15 or whatever, if you can find a perfect square factor, grab it out, because then you'll be able to simplify. Well, if you're playing with cube roots, these are all cube roots. If you're playing with cube roots, you need to have perfect cubes. What are perfect cubes? 8's a perfect cube because the cube root of 8 is 2. And by the way, -8 is a perfect cube because the cube root of -8 is -2, right? So 8 is a perfect cube. 27, whether plus or minus, 27 is a perfect cube because it's 3 times 3 times 3. This one's fun. 64 is also a perfect cube because 4 times 4 times 4 again comes out to 64. Can you guess what I did to get a 125? I did 5 times 5 times 5 again. And if you wanted to generate more, you could take 6 times 6 times 6 again, which I think is 216 if I'm remembering right. So anyway, hunting out. If you have a cube root radical, see if you can sniff out, so to speak, one of these numbers over here, one of these perfect cube numbers. Let's get a different color going. Yeah, gray, what the heck. Let's get a different color going here. Yeah, purple, what the heck. Cube root, 16. 16, huh? Does 16 have an 8 in it? Does 16 contain a factor of 8? It does. 16 contains a factor of 8. So I'm going to think of this as an 8 times a 2. So I don't usually write this part out, but I will. What's going on here is we're saying that the cube root of 16 can be rewritten this way as the cube root of 8 times the cube root of 2. So notice, if you multiply cube root of 8 times cube root of 2, you can just multiply the 8 times the 2 to get the 16. You get the cube root of 16, right? It's the factoring property of radicals. You can break them apart like that. But anyway, the reason we did that is because this part can be simplified. Simplified means I don't have to use that crazy radical symbol anymore. The cube root of 8 is just a 2. 2 times 2 times 2 is 8. Good, I simplified it. Now this is supposed to be times this, and I can't simplify this, so I just have to write it the way it is. There's our answer right there. Okay, so the cube root of 8 simplified to a 2. That's what enables us to simplify this radical down to this. Okay, hunt out the perfect cube. Here's another cube root, so I'm looking for perfect cubes. Does 8 go into 54? Well, not really. 8 times 6 is 48. That's close. 8 times 7 is 56. That's close. No, it doesn't go. Okay, we're not going to use the 8. Can we use the 27? Does 27 go into 54 evenly? And the answer is yes, it does. 27 times 2 is 54. So once again, I often skip this step, but I'm going to write it here just for clarity. What I'm saying is that the cube root of 54 is the same as the cube root of 27 multiplying the cube root of 2. So again, 27 times 2 is 54. So the cube root of 27 times the cube root of 2 is the cube root of 54. Cool. And the reason I did this again is because this part we can simplify. We can do something there. We can get rid of that funky looking symbol, the cube root symbol, because the cube root of 27, or I should say the principal cube root of 27, is just 3. So that's a 3, and I still have this times a cube root of 2 here. That doesn't go away or anything. And so there, I found a 27. Let's look at this next one here. 250, does it have an 8? No. Does it have a 20? No. No. You know what it has? It's got a 125 in it. See that? It's got a 125 in it. That's what we should do. And in fact, because it's a negative, I'm actually going to break it up as a negative 125 times a 2. So what I'm saying here is that the cube root of negative 250 is the same thing as if I had the cube root of negative 125 and I multiplied it by the cube root of 2, right? So once more, negative 125 times 2 is negative 250. So it works. So the reason is because this part can be simplified. A cube root of negative 125. What times itself is 125? And the answer is not just 5, but negative 5, right? Negative 5 times negative 5 is positive 25. But then positive 25 times negative 5 is negative 125. Woo-hoo, city. Don't lose this. It's times the cube root of 2. And there's our answer there. So it would work, of course, the same for fourth roots. And so if you had a fourth root radical, you'd say, well, what are my perfect fourth powers? 2 times 2 times 2 times 2 is 16. 3 times 3 times 3 times 3 is 81. You can just work out the list yourself if you want to do it that way. There is an alternative, of course, and that alternative is the old busted up with the sledgehammer trick, the old prime factorization method. Here you're trying to bust up a number, factor it down until you get all primes. Primes are 2, 3, 5, 7, 11. You might have to do a 13 someday, who knows. So those are the prime numbers. So what you're doing is you're saying, okay, let me pulverize this 81, and I'll start by trying to divide by 2. Except 81 is odd, so 2 is not going to work, so never mind. Okay, I'm going to start by dividing by 3. Does 3 go into 81? And it does. It goes 27 times. Now, the 27 can be divided by 3. See, I want to keep using the 3 over and over and over again. And then the 9 can be divided by 3. And so what we've got here is the 81 became 3 times 27. The 27 became 3 times 9. The 9 became 3 times 3. What I got here is 3 times 3 times 3 times 3. Now, 3 of a kind is what you need to be able to take a cube root. So I'm going to sort of think of these as one group and then this. So the cube root of 81 is the same as the cube root of 1, 2, there's 3 of those. And the cube root of, and I still got this one. Okay. So the reason you're pulverizing it down into its primes is because you want to gather together any triples you could find. And the triples you're going to write separately. So I got a triple of 3s. I got 3 to the 3 power. Okay, write that part separately. Put it in its own cube root. You have to, of course, not lose any pieces. I still got this other 3, so okay, I still got this other 3. But the reason we did that, again, is because this part can now be simplified. The cube root of 3 cubed is 3. 3 times 3 times 3 is 3 cubed. So the cube root of 3 cubed is 3. Don't forget this other leftover part. Okay. So that's another nice approach you can take to simplifying these things. Now, if the numbers are kind of big and weird looking, this might be the approach you want to take. Let's go back to purple. Looking at the 144. Well, if I were going to use my prime factorization strictly, I would start by dividing by 2. I'd divide by 2 over and over and over and over until I couldn't anymore. Then I would divide by 3 over and over and over until I couldn't anymore. Then I'd move on to the 5 and so on. If you like being, what's the word for that, methodical? If you like being methodical like that, you might, well, sometimes I like to be methodical. But sometimes you just kind of like to go like this. You say, 144, hey, I know what that is. That's a 12 times a 12. Now, 12s are not primes, but so what? It's broken up a little bit. Yay! But now you have to keep breaking up the 12s. In fact, you have to find primes. So the 12, well, I'm going to say it's 3 times 4. Why? Because I feel like it. It's 3 times 4. But I have to keep going until it's all primes. See, that's the trick. So this 12 is now a 3 times 4. This 12 is now a 3 times 4. Okay, this 4 is a 2 times 2, right? And this 4 is a 2 times 2, right? So what have I got here? I've got a 3 and a 2 and a 2 and a 3 and a 2 and a 2. Now, I'm taking a cube root, so I want to gather together 3 at a time. So what am I going to write? I'm going to write the cube root of. I can grab 3 2's right here. 1, 2, 3. And that's going to multiply. And what have I got left? I only got a pair of 3's. That's a bummer. Just a pair of 3's. And then I just got this single leftover 2 left. So those are my leftovers in there. I'm not going to be able to simplify any of this because nothing has an exponent of 3 on it. So I can't do anything with that. But this part I can simplify, right? The cube root of 2 cubed is just 2. And then over here, you might as well multiply that back together. 3 squared is 9. 9 times 2 is 18. And so there you go, 2 cube roots of 18. So the moral of that story is when you're doing the prime factorization method, you can really either do it methodically, where you start with the 2, keep using the 2 until you can't use the 2, and then you use the 3, and then you keep using the 3 until you can't use the 3, and then you move on to, and so on. You can be methodical, or you can be a little more freestyle. Hey, 12 times 12, woohoo! Hey, 12 is 3 times 4, woohoo! But just make sure that the apples at the bottom of your branches here, so to speak, these are all primes. These all have to be primes. In other words, in the end, you need to have nothing but 2's or 3's or 5's or 7's or anything like that. Okay. Let's see now here. Here's another one. Negative 108, huh? Well, first of all, we make it a little bit easier on ourselves. Think of it as a negative 1 times a 108, right? In other words, the cube root of negative 1 is just negative 1, or the principal cube root is negative 1. So when you take the cube root of a negative, you're going to get a negative answer, is the bottom line. Negative. Right, so I'm just kind of taking the negative straight through the radical because, again, the negative is like a negative 1. The cube root of negative 1 is negative 1. We're good. Now let's start breaking up that 108. And I think I'll go methodical again. I can divide by 2. Yes, I can. 2 goes into 108 54 times. 54 is even. I can divide by 2, and I get 27. Guess I'm done with the 2. Okay, 3. 3 goes into 27 9 times. 3 goes into 9 3 times. So I'm done with that, done with that, done with that. So notice what I got here. I do have a 3 of a kind right there. I have 3 3's. So I've got the negative in front. Don't lose it. I've got this 3 cubed, which I will gather together into one of my radicals. And then I'm going to have to put all the leftovers back in another one. So I got the 2 and I got another 2. Let's just call that a 4, I guess. 2 times 2 is 4. And so I've got negative. When you take the cube root of 3 cubed, you get 3. And then a cube root of 4 left over. And there's our final answer. Pardon me. So you notice it's very hard to keep using the language precisely. I should be saying things like, the negative principal cube root of 3 cubed is, negative 3, whatever. The word principal keeps falling by the wayside, but you need to keep in mind, when we're playing with these radicals, we're always talking about principal roots. Okay. Hey, you want to try a 4th root? Same idea. It's just that instead of 3 of a kind, you need to have 4 of a kind. Actually, I would invite you to pause and try all 3 of these. Try all 3 of these. and then see how close you get. Because, the way to make sure you're learning this stuff is, watching is one thing. But when you're watching, you tend to fool yourself and say, yeah, I followed all that. I must understand. But it's when you do it that you say, wait, I'm getting stuck at this point. And then getting unstuck. That's where the learning happens, is when you get yourself unstuck. So you have to try to get stuck as often as can so that you can get unstuck and learn. Okay? Try to get stuck. It's good theory. Anyway, you ready? 4 through to 96. I'm going to start by prime factorizing. I can divide by 2. That would give me a 48. 48, I can divide by 2. That would give me a 24. 24, I can divide by 2. That would give me a 12. 12 is 2 times 6. 6 is 2 times 3. So, these numbers have been broken apart. Don't look at those. But what do we got here? We got all kinds of stuff. We got all kinds of stuff here. Let's gather together 4 of these. Right, because we're talking about 4th root radicals. So I've got the 4th root of, and that's a 2 to the 4th. Now I don't have any more sets, so I'm just going to have to put the leftovers back in here. And I could write 2 times 3, I suppose. 4th root of 2 to the 4th, principle. 4th root of 2 to the 4th is 2. And then this is going to be a 4th root of, just call it a 6. And there you go. This a 1. Hey, that's a 96. That's the same thing. So I know how it's going to break up. It's going to break up as I had a 2 times a 2 times a 2 times a 2. What do I have? 1, 2, 3, 4. I had 5 of those. Times a 2 times a 3. That's what the 96 is. Now I'm looking for, since it's a 5th root, I'm looking for sets of 5. So it just so happens I do have a set of 5. Those will go in their own radical. 2 to the 5th like this. And then I still got a 5th root of this 3 is still left kicking around. So the principal 5th root of 2 to the 5th really is 2. And then I've got a 5th root of 3. Negative 486. Oh my goodness. Well, again, I know the answer is just going to be negative. Let me just put that there. There, that was easy. An odd root of a negative always comes out negative. The principal odd root of any negative number always comes out negative. So it's as though the negative can pass through. Don't you dare do that for a square root or an even root. But for odd roots, it works. So now I got to break up the 486. Okay, 486, huh? Well, I guess I'll start with 2. 2 times, what is this, 243. Well, guess I'm done with the 2 already because that's odd. I can't divide by 2 anymore. It looks like it's up to me to divide by 3. 3 times what? Well, 3 into 24 is 8. Okay, that worked. Cross that off. Okay, now the 81 can be divided by 3. You get 3 times 27. Cool. 27 can be divided by 3. You get 3 times 9. Once you get going on these things, they get easier and easier, right? Because the numbers get smaller and smaller. That's the good news, at least. So 5th root, eh? Guess I'm looking for a set of 5. 1, 2, 3, 4, 5. I do have a set of 5. Cool. That means I can write this as, let's see. First of all, the answer is going to be negative. Let's not lose that. 5th root of, I had a set of 5 3s. So 3 times 3 times 3 times 3 times 3. 3 to the 5th. And then times, we still got a 2 kicking around, so don't lose that part. So, again, the whole reason we're doing this is to allow us to simplify at least some of this stuff. The 5th root of 3 to the 5th is 3. Don't lose the negative there. Negative 3 times the 5th root of 2. There she blows. So this factoring tree method or prime factoring method or whatever you want to call it, when you've got some nice numbers that you need to chew on, it's not a bad way to do it. You take the big number, you smash it down into its small little prime bits, and then you just look for sets. If it's a 5th root, I need a set of 5 if I'm going to simplify. By the way, if I couldn't find a set of 5 anything, I'd say, I guess I can't simplify. What are you going to do? Can't simplify. Okay, now we got to bring in our x's. Bring in our x's. Bringing in our x's. Okay, so across, actually these are all cube roots on the rest of this page. So that keeps it nice, at least in some sense. It's all cube roots. Focus on the cube roots. Think back to square roots actually for a second here. Remember when we did this, we said, hey, the square root of x squared is, well, we had to say this. But it was basically you cut the exponent in half. 2 divided by 1. is 1. If you had x to the 4th in a radical, all you had to do was cut your exponent in half. 4 divided by 2 is 2. And I don't need absolute value bars here because x squared is going to be positive no matter what. But if I had x to the 6th, all I had to do was cut my exponent in half. That's the part I'm trying to get you to focus on. The 6 divided by 2 is 3. Just cut the exponent in half, and in this case, absolute value bars to make sure that the right side is positive. Anyway, when you're doing square roots, you're basically just cutting the exponent in half. Well, guess what? When you're doing cube roots, you're basically just dividing the exponent by 3. Divide the exponent by 3. Let's even write that down. Divide the exponent by 3. Smiley face. And so this is just x. Bum, ba, bum, bum, ba, bum. It's just x. And to prove it, the question here is what times itself again gives me x cubed. And of course, x times itself again gives me x cubed. And remember, with odd roots, I don't have to worry about any of this stuff, because if x were a negative 2, if I had a negative 8 inside, my principal root would be negative 2. So I don't have to worry about whether I'm getting a positive. If I plug in a negative x, I'm going to get a negative answer, which is what I want. I'm not going to have to worry about absolute value bars. Anywho, so back to the main point. Divide the exponent by 3. I get x squared. Woohoo! Divide the exponent by 3. I get x cubed. 9 divided by 3 is 3. X cubed. Again, the proof is in the pudding. No. This times itself. Remember, you'd be adding your exponents here. 3 plus 3 plus 3 is 9. And that's why we're dividing. It's kind of like the opposite. It's, 9 divided by 3 is kind of like saying, what's the number that I have to add to itself 3 times? The answer is 3. X to the 10th. Uh-oh. Here's the problem. 10 doesn't divide by 3 very nice. It comes out to what? 3 1/3. Okay, it doesn't come out really nice. But the 3 is telling you something, or not that 3, this 3. This 3 is telling you something. It's telling you I will be able to get at least 3 sets. Here's what you might want to do is break off the closest multiple of 3. What we were showing up here is that if you have a multiple of 3, x to the 3 comes out even. 6 is a multiple of 3, and it came out even. 9 is a multiple of 3, and it came out even. If you have x to the 3, x to the 6, x to the 9, x to the 12, x to the 15, x to the 18, all of those things, if you count by 3s, their cube roots come out even. So here, I got a 10. Well, the closest I can get is 3, 6, 9. I can get to 9. So I split off the x to the 9th. Now, of course, it's x to the 10th, which means I have to really write it this way. So it's the cube root of x to the 9th times the cube root of x. So again, x to the 9th times x gives me x to the 10th. That's why it's legal to break this up this way. Ooh, that's not what I wanted to do. Oh, darn. There we go. Use the eraser. There we go. So you split it off like this, and the reason is because this part can be simplified. 9 divided by 3 is 3. And so the cube root of x to the 9th is x to the 3, and then it's times the cube root of x like this. Okay, so here's the main point right there. Break off the closest multiple of 3. So that's what I'm going to do here. I'm going to break off the closest multiple of 3. So you start by counting by 3s. 3, 6, 9, 12, and then 15 is too far. So 12. 12 was the closest I got. So break this off as 12, and then you still got, because it's 14 here, you still got 2 more, right? You got to make sure that this times this equals this. So this is x to the 12th times x to the 2 will give me x to the 14th. Okay, so this is a legal way to break it up. Boink, 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 boink. Okay, that's a legal way to break it up. Again, the reason we're doing it is because this part simplifies. That's the whole goal, is to simplify something. 12 divided by 3 is 4. The cube root of x to the 12th is x to the 4th. And once more, if you multiplied x to the 4th times itself 3 times, you would be adding your exponents. 4 plus 4 is 8, plus 4 is 12. You would get x to the 12th. So yeah, it works. So that part simplifies to x to the 4th, and then you just have to keep all your pieces. Don't lose any pieces. I've still got my cube root of x squared here. Okay, with this one, once more, it's an odd root. The negative is basically going to pass through. And, oh, here's the good news. Counting by threes until you get to 15. 3, 6, 9, 12, 15. It comes out even. So actually, we don't have to do anything else that's weird here, or that's fancy here. We can just kind of say, hey, man, it's going to be negative, and it's going to be 15 divided by 3 is 5. This comes out to negative x to the 5th. That's all there is, and there ain't no more. Okay, trying to get this to be the right width. So that's how you can deal with the x's. So again, if you're taking a cube root, count by threes and get as close as you can. By the way, if you're taking the fourth root, you would count by fours until you got as close as you could. If you were taking the fifth root, you would count by fives until you could get as close as you can, and so on. That's the basic idea. Looks like we got some more cube roots for a little while. Okay, so this is mixing it up a little bit. Cube root of x to the 8th. This is one of my favorite test questions, because you have to keep in mind that you're doing different things with those 8s, right? Because this 8, well, we call it a coefficient. It's just a number. But this 8 is an exponent, and you handle these completely differently. You don't really handle the, well, yeah, you do. You handle x to the 8th. Anyway, the cube root of 8, we can do that. It's just 2. 2 times 2 times 2 is 8. So that's nice. Again, you're not going to take the cube root of that 8. That's not how you play with those things, right? So that's the most common wrong answer. What you got to do here is you got to take the x to the 8th, and like I was saying before, you got to count by threes and get as close as you can. 3, 6. That's as close as I can get to an 8 without going over. So I got a cube root of x to the 6th split off, leaving, and you know, this has to be an x squared because you need this times this to be this. So x squared times x to the 6th is x to the 8th. That works. Okay, cool. So get rid of that, get rid of that, get rid of that. Now the whole reason we did this, again, is because we're looking for a piece that we can simplify. This piece we can simplify because if you take 6 divided by 3, you get squared. So I got my 2 out front. That becomes an x squared, and this is stuck here as an x squared. And there she blows. Cool. Huh. Here, the 16 x to the 16th. Again, that's a 16, that's a 16, but we're playing very different games with our 16s. Let's see now here. With this 16, I'm going to say, well, that's an 8 times 2, because I know I can take the cube root of 8. So that's called sniffing out a perfect cube. You could do the tree method if you want, and you would gather together, you know, 3 2s, and you'd have a leftover 2 over here. It's going to come out the same either way you do it, of course. But I'm going to break that off as 8 times 2, and then the x to the 16th. Remember, with exponents, you want to basically count by threes and get as close as I can. So 3, 6, 9, 12, 15. I can get to 15. So I'm going to break that up as x to the 15, and it'll have to be times another x. Once more, x to the 15 times x to the 1 is x to the 16. You need to make sure you've got all your pieces there. So now I can think of all of these as in cube root, I guess. Maybe I'll write it like this. They're all in the cube root, but some of these pieces are getting simplified. You can simplify the cube root of 8 and get a 2. You can simplify the x to the 15th part, right? Take the 15 exponent, divide by 3, and you get 5. So those are simplified. They're outside the radical now. They've been simplified. The stuff that's not simplified has to stay in the radical because, well, I couldn't do anything with it. I got a 2, I got an x. Put those back in there. Here we are. Cool. I wonder if you'd be willing to stop and try the remaining 4 of these things. There's a cube root. There's a 4th root. There's a 4th root. There's a 5th root. But give them a twirl. See if you're catching on. See if you get stuck. Remember, that's how you learn, is by getting stuck and then unstuck. Okay, back already? Cool. Hey, I want blue. Okay, first of all, it's an odd root of a negative. It's just going to come out negative. Let's deal with the 24 and the x to the 5th. Now the 24, remember my perfect cubes are like 8 and 27 and so on. Does the 24 have an 8 in it? It sure does. So I'm going to think of that as an 8 times 3, because that I'm going to be able to simplify in a minute. X to the 5th, if you count by threes, the closest you're going to get is x to the 3. And you'll need an x squared, right? Because you need x to the 3 times x to the squared is x to the 5th. You need to be able to say that what you wrote on this line is exactly the same as what I wrote on the line above. And it is exactly the same if you think of it as all inside a cube root. Now comes the part where I can simplify some of these things, right? The cube root of 8 can be simplified. To simplify, it would become a 2, and it will be out here now. It's not inside a cube root anymore. I'm cube rooting it. If you cube root it, it gets out of the cube root, right? It's a 2. And the same thing here. If you take the cube root of x cubed, you get an x. Out of the radical. It's gone. It's free. But then you have leftovers. So you have to put your cube root radical back to contain all the leftovers. You got a 3. You got an x squared. There you go. Oh, don't. I've got to remember my negative out front, right? That came from up here. Don't forget the negative. Okay, what do we got here? 4th root of 16x to the 16th. Well, in terms of numbers that have, that come out evenly, 2 to the 4th would be 2 times 2 times 2. That would actually be 16. So actually, that's a perfect 4th right there. This 16, you have to divide by 4, right? Exponents, you divide by 4. This actually comes out even. Whoops, not that. This actually comes out even. The 4th root of 16 is 2, and the 4th root of x to the 16th is x to the 4th, right? Again, the main point is, that's why this makes such a good test question, you see these two 16s, but you have to remember to deal with them in very different ways. This one, I'm actually taking a 4th root of the number 16, and I'm getting 2. 2 times 2 times 2 times 2. But this one, it's not a 16. It's an x to the 16. What times itself times itself times itself is x to the 16th. It's x to the 4th. And by the way, it's not a bad idea when you get an answer. If you have any doubt in your mind, you can always just check it. You were trying to take a 4th root. So what you're saying is that this times this times this times this is going to give me the 16x to the 16. Will it? Well, the 2 times 2 times 2 times 2 is a 16. That works. And when you multiply all these x's together, you're adding your exponents, right? 4 plus 4 plus 4 plus 4 would give you x to the 16th. It's working. You can always spot check to make sure you got it right. No sense just guessing and hoping. You can actually check it. You can actually check it. Well, this is a 4th root. Okay, so I can use this again. This fact over here, I know that 16 is 4th rootable. So when I see a 32, what jumps to mind is that, hey, that's 16 times 2. And I'll be able to simplify the 4th root of 16. So let me just break up the 32 as a 16 times 2. As for this x stuff, exponents, remember you have to count by 4s and get as close as you can to 7. And that's really all it. You 4 and then 8. 8 you've gone over. That's too far. So you have to take x to the 7th, break it into 2 parts. This part we're going to be able to simplify, the 4th root of x to the 4th. This part we're not going to be able to simplify. But again, the main point is that x to the 4th times x to the 3rd is x to the 7th. So yeah, it's legal to break it apart that way. And now I'm going to be able to take this and simplify it. I'm going to be able to take this and simplify it. Now, just to be official, this is still all underneath a cube root. But when I process the not a cube root, I'm sorry, 4th root, root, mistake alert. Okay, that was a 4. That was such a 4. Okay, 4th root. Anyway, I'm going to be able to take the 4th root of 16 and just get a 2. See, I'm processing it. It comes out, right? 4th root of 16 is just a 2. The 2 comes out. 4th root of x to the 4th is just x, right? X times x times x to the x is x to the 4th. Or you can say 4 divided by 4 is 1. That comes out. It's out. Okay. This other stuff can't come out. It's stuck in there forever. It's stuck inside my 4th root radical. I got a 2, I got an x cubed that are all stuck in there. So put them in there. And there you go. There you go. By the way, how would I check this answer to make sure it came out right? Well, I'm trying to say that the 4th root of this is this, and that means that this times itself 4 times should give me that. So let's just make sure that works. Get this stuff out of the way. Let's just make sure that really works. So if I took a 2x times a 4th root of 2x cubed, and I'm going to say multiply it by itself 4 times, but if you don't mind, I'll just put a 4 on it like that. So 2 to the 4th power is 16. X to the 4th power is this. And then the 4th root radical raised to the 4th power, it's kind of like canceling each other. They're inverse operations is what we would call them. So that was a 4, that was a 4. So the 4 and the 4th root kind of cancel each other, giving me this 2x cubed. And so notice when you multiply this, you get the 32, and when you multiply this, you get the x to the 7th, and that's what we had. So yes, it's actually checking your answers is, why did I erase that? That's not, I don't have to erase that, that's cool. So checking your answer is like, it's a good idea, because you can do it. You can make sure you're getting the right answer. This one. Okay, maybe the 64, maybe I'll just start busting it up. I know it's 8 times 8. I know the 8 is a 2 times 4. I know this 8 is a 2 times 4. I know this 4 is a 2 times 2. I know this 4 is a 2 times 2. Look at all those 2's. Look at all those 2's. So I want sets of 5. So I can think of this as the 5th root of 1, 2, 3, 4, 5. Make sure you don't lose any. And then I've still got one left, so don't forget that one either. Make sure you don't lose any pieces. So that's how I'm going to break up the 64. Now as far as the x to the 8th goes, so again, with these x things, you are going to count by 5s and get as close as I can to the 8. And x to the 5th is as close as I can get to the 8. So the x to the 8th is going to be x to the 5th times x cubed, right? So x to the 5th times x cubed is x 8th. Yep. All good. So, I did it a little bit differently. Instead of writing one big giant radical, I actually wrote all these separate radicals. But it's exactly equivalent. Exactly equivalent. The point is what you can do on the next move, and that's simplify some of this stuff. So the 5th root of 2 to the 5th, it's a 2. The 5th root of x to the 5th, it's an x. Do those first. Now gather together your leftovers. I got a 2 here, I got an x cubed here, I got a 2x cubed. And there you go. And I'll invite you to raise that to the 5th power and make sure it checks. Okay, so as before, the last main move we got to look at is rationalizing denominators. And then we'll summarize by saying, what is simplified radical form anyway? Rationalizing some denominators. Oh, I'm going to have to take a sip. Okay, this is a blast from the past. You got to square root of 2. Remember, we don't like radicals in our denominators. So the way we were able to get rid of that is we just sort of made a duplicate, right? If you multiply root 2 times root 2, you just get regular 2. And I don't have a radical in my denominator anymore. And now I'm happy. Okay, so root 2 times root 2 equals root 4, I guess. But the root 4 is just 2. So copying it makes it just a 2. On top, I got 1 times root 2. So here we go. So this is an irrational denominator. Square root of 2 is an irrational number. If you plunk it on your calculator, the decimals are not going to stop. There's not going to be any pattern. It's kind of like pi in that regard. Square root of 2 is an irrational number. So that's an irrational denominator. What we did was we fixed it so that we have number 2 is a rational number. Its decimal just repeats forever, 0.0000. So this is a rational denominator. So see what we did? We took an irrational denominator, turned it into a rational denominator. Now do you see why we're saying this? We're rationalizing our denominators. Woo! Anyway, that was the trick that works. Works for square roots. Works all the time for square roots. So the first thing I have to point out over here is that it's not the same thing for cube roots. Now I would ask you to just watch for a second. Do not write this down. If you write this down, you're going to get muscle memory problems. You're going to always do it the wrong way. Don't always do it the wrong way. Equals. If I were to do what I did here, which was to basically make a duplicate and multiply top and bottom, right? If I do that here, does that actually work? Does it actually work? 1 times the cube root of 2 is the cube root of 2 on top, fine. But the cube root of 2 times the cube root of 2 is not 2. The cube root of 2 times the cube root of 2 is the cube root of 4, and the cube root of 4 does not come out even. Oh. See, here's the thing. When you're doing this, when you get to this, quote, advanced math, unquote, you have to go past the, muscle memory? You have to go past the just looking for patterns and duplicating patterns and saying, yeah, when I get in this situation, I just make a duplicate. Yeah, I'm going to do the same thing here. I'm going to make it, it looks kind of similar. I'm going to do the same thing. Yeah. You can't, you have to actually take a close look at what you're doing and make sure that what you're doing is working the way you want it to. This is not working the way we want it to, right? I just showed you that. The cube root of 2 times the cube root of 2 is the cube root of 4, and that we can't simplify that. We struck out. It doesn't work. Uh-oh. So what are we going to do then? We need a new thing. We need a new thing. We need a new color, and we need a new thing. The new thing is to say, well, look back here for a second. Why did this work? This worked because 2 times 2 is 4, and the radical 4 really is 2. That's why it worked. We built up a square inside of our square root radical. 4 is square rootable. So since it's square rootable, the square root goes away. Well, if this is a cube root, I need to build, not a square, I need to build a cube inside. Build a cube inside. How am I going to build a cube inside? Well, you might think of 2 as just 2 to the 1. So to get it to be cubed, you would want to multiply top and bottom not just by 2, but by 2 squared. Get it? 2 squared. Because when you multiply cube root of 2 times the cube root of 2 squared, that would be the cube root of 2 cubed. You can call that an 8 if you want. 2 squared is a 4, really. But the point is that this does simplify. The cube root of 2 cubed does enable us to simplify. That's the whole point. We want to simplify so that we don't have any funny radical symbols anymore in our denominators. So the top is going to be a cube root of 4. The bottom is going to be just a 2, and we have succeeded. Now we have succeeded. So this turns into this. Again, this is an irrational denominator. Cube root of 2 does not come out even at all. This is a rational denominator, so we've rationalized our denominator. And it's etiquette. It's just like reducing fractions. You want to reduce your fractions. It's etiquette. It's good. You just reduce them. You just do it. And radicals in the denominator, no. You don't do that. You rationalize. You rationalize. And now you know the secret for rationalizing with cube roots. Okay, let's look at another couple examples. These are cube roots. These are got a bunch of cube roots and then a 4th root. Okay, some more cube roots. So, once more, our goal is to build this up to a cube. It's not a cube right now. If it was a cube, I'd be able to take the cube root and wouldn't have this problem. But it's not a cube, so I have to build it up to a cube. Now, tip. You could think of that as 4 to the 1 power, which means I have to multiply by 4 to the 2 power. But think of the 4 as a 2 squared. Right? You already have a 2 squared. That's pretty cool. So think of the 4 as a 2 squared, and then you don't have to multiply by as much stuff. If I want to build up a cube inside, this is going to need another 2 to make it a 2 cubed. X is going to need to be multiplied by x squared to make it x cubed. So there's the trick. We're multiplying top and bottom by the cube root of 2x squared. Now I usually skip this part, but I won't. I'm just going to prove. 2 squared times 2 is 2 cubed. X times x squared is x cubed. Okay, that was the whole point, was to put cubes inside. And then on the top, I've just got 1 times that. And so the final answer is, the top, can't do anything with the top, just leave it there. But the bottom, we built something that we could simplify. That was the whole point. So the cube root of 2 cubed is 2, and the cube root of x cubed is x, and there we are. There's our nice rationalized denominator form. Cool beanie weenies. Cool beanies, cool beanies. Let's look at this one over here now. I need to build this up to a cube. Actually, what I might want to do is simplify first. Because x to the 4th, see, this exponent is bigger than this exponent, and that's a clue that, wait, this should be simplified. This should be simplified. So, and then the 24. Remember our list of perfect cubes, 8, 27, and so on. 24's got an 8 in it. So let me simplify first. So I'm going to think of the 24 as an 8 times a 3. And then I'm going to think of the x to the 4th. If you count by 3s, you'll get to 3. And then you'll still have an x left, right? Because again, the point is x to the cube times x gives me the x to the 4th that I have here. Okay, so this is allowing me to simplify. So I got it 1 over. Now the cube root of 8 simplifies to just 2. The cube root of x cubed simplifies to just x. And now I've got some cube roots. 3 and an x are left over. Cool. So first I simplified, and I got to there. Now you switch colors, and you say, okay, build this to a cube. Build this to a perfect cube. Multiply top and bottom by the cube root of something. But remember, with square roots, you just make a copy of what you see. But with cube roots, you have to actually kind of think about it a little bit and say, look, I need to build to a cube. That's 3 to the 1. I'm going to have to multiply by 3 to the 2 so that I have 3 to the 3. Okay, you have to build to a cube. I have x to the 1. I'm going to have to multiply by x squared to make it into x cubed. Okay, cool. So on the top, I got a 3 squared x squared as well. Multiply top and bottom by the same thing. What do you get? Well, 1 times this is this. And I might as well call that a 9x squared. Okay, cool. On the bottom, what have I got? Well, you get your 2 times your x, and then your 2 cube roots multiply together to give you a 3 cubed x cubed. And then we can go a little bit further with this. And I mean, this was the whole point. We wanted to be able to simplify this, right? So this, and I think I'll change colors so it's easier to follow the action. Change colors. The cube root of 3 cubed x cubed is 3x. You've got this 2x multiplying this 3x. So our final answer then on the top is a cube root of 9x squared. And on the bottom is a 2x times a 3x is a 6x squared. Woo! We did it. We went and did it. We went and did it. Okay, so there's 2 more examples here. And once more, I'm going to pause and ask you to try these yourself. See how far you get. Okay, back to green. First of all, I want to simplify first. 8 is much bigger than 3. That's begging for some simplification right there. But also the 54, yeah, that's got some cubes in it. Let's see now here. Remember the perfect cubes. Come on, phone. The perfect cubes are 8. 2 times 2 times 2 is 8. 3 times 3 times 3 is 27. That's another perfect cube, and so on. Looking at the 54 here, I spy a 27. So I'm going to break up that 54 as a 27 times a 2. Okay, cool. As for this x to the 8th, remember with exponents, I'm counting by 3s until I get as close as I can get. The closest I can get is 3/6. It's the closest I can get. So I'm going to also have an x squared here because, again, I need to make sure x to the 6th times x to the squared gives me the x to the 8th. Right. Okay, cool. So starting to simplify now. This part gives me just a 3. This part gives me just an x squared. And then I've got stuff still trapped inside cube root radical here. I've got a 2 and I've got an x squared. Cool. So, boy, this is taking some room, huh? So what I'm actually looking at is 1 over, and I've got a 3x squared, and I've got a cube root of 2x squared. Okay, cool. Now comes the part where I need to build up to a cubes. This is the part where you multiply top and bottom by the cube root of something. But again, with square roots, you just look at it and you make a copy. With cube roots, you have to think it through because you're trying to build up to cubes. You have to stop and ask yourself, I've got 2 to the 1. I'm going to have to multiply by 2 to the 2 because 2 to the 1 times 2 to the 2, you would add your 1 and 2 and get 2 to the 3, right? X squared. Well, I'm going to need to multiply by another x, just an x, because x squared times x will give me x cubed. Okay, cool. So I'm multiplying top and bottom by cube root of 2 squared x. What does that give me? On the top, it gives me the cube root of, and I might as well call that a 4x. And on the bottom, it gives me a 3x squared, and then it gives me a cube root of, and when I multiply 2 to the 1 times 2 to the 2, I get 2 to the 3, and when I multiply x to the 2 times x, I get x to the 3. this part simplifies right here. This was the whole point, was to be able to simplify. So 2 cubed cube root is 2. X cubed cube root is x. I got a 3x squared multiplying a 2x. So the top is a cube root of 4x, and the bottom is, I get 3x squared times 2x, which is 6x cubed. Woo! Thirsty work! Boy, we're earning our homework tonight. Okay, cool. That's cool. One more of these, just to put a fourth root in there, just for giggles. I'm going to try to get this stuff kind of out of the way somehow. Shrink. What are you doing? Shrink yourself. That's not so bad. Okay, back to here. Fourth root, huh? Oh, this raises another one of those reminder type points. It's a fraction inside of a radical. Well, think of it this way. Okay, you have to think of it this way. In other words, I keep saying never let a radical stay in your denominator. Well, this might not look like we have a radical in the denominator. It looks more like we have a denominator in the radical. But actually, that's the same problem, really. It's the same as having a radical in the denominator. So don't leave fractions inside radicals either, is the point here. So the fourth root of 1, or the principal fourth root of 1, of course, is just 1. So that's what the top is. The bottom is going to be the fourth root of... Now, 9. I'm going to think of that as a 3 squared. Save me a little work. Because we're going to have to build up to a fourth power. And do I want to multiply by 9 cubed to make it 9 to the fourth? Not if I can do this instead. If I've got a 3 squared, I only have to multiply by a 3 squared. So, yeah. Look for that. Look for, chances to take that number and write it as the square of something or the cube of something or whatever. So 9 is 3 squared, cool. And then x to the 6th, I know that's bigger than 4, but I'm just going to leave that here because I'm going to show you a little trick that I sometimes do. So this is what we're looking at, 1 over the fourth root of 3 squared x to the 6th. And what we want to do is we want to build up to a perfect fourth. I don't know what you would call that. Build to a perfect fourth power, I guess is what I'd say. Build up to a perfect fourth power. So I'm going to multiply top and bottom by the fourth root of something. And the question's going to be the fourth root of what? Well, again, I'm trying to make this be an exponent of 4. It's already an exponent of 2, so I'll need 2 more, right? 3 squared times 3 squared will be 3 to the fourth. Now this 6, like I say, the 6 is already bigger than 4. But that's okay, because what I'm going to do is, remember you count by 4s? I'm going to say 4, 8. I'm going to build that up to x to the 8th. So in other words, I'll multiply by x squared, top and bottom. In other words, just build to the next multiple of 4. So 4, 8. Build this up to an 8. Make it an 8. I want an 8. If I make that an 8, I'll be able to simplify, and that's all I really care about, is being able to simplify. So what do I got now? On the top, I've got a fourth root of. And I might as well call the 3 squared a 9, x squared. On the bottom, what have I got? I got a fourth root of. Now the 3 squared times the 3 squared is a 3 to the fourth. And an x to the 6th times an x squared is an x to the 8th, actually. But that's okay, because now I can simplify. By the way, that's an 8. So now I can simplify, because the top is, well, it is what it is, fourth root of 9x squared, fine. The bottom is, you take the fourth root of 3 to the fourth, you get 3. You take the fourth root of x to the 8th, remember 8 divided by 4, you get x squared. And so actually this problem was shorter than the one before it. So look at that, fourth root of 9x squared over 3x squared. Okay, cool. Well, we're going to end with a reminder. We've been doing this the whole time, it's just that I haven't been saying it outright. But I'm going to say it outright so that you can keep this in mind when you're doing your work. How do you know when you're done with a problem or not done with a problem? You're done with a problem when it's in what's called simplified radical form. And by the way, that's always going to be the instructions. You express in simplified radical form. Or it'll say, do a bunch of things, and then express your answer in simplified radical form. Okay, we need to know what that phrase means, simplified radical form. First thing it means is all radicals are simplified. I guess that part seems logical, right? Simplified radical form means that radicals are simplified. And I'll just put e.g. if you had the square root of, I don't know, 8, you would not write it as a square root of 8. You would write it as a square root of 2 square roots of 2, 2 radical 2. You do enough of these, you start to see this immediately. If you don't see that immediately, that's fine. You're new at this. But the 8 is a 4 times 2, get it? And the 4, I can take the square root of 4 to get the 2 here, and then this is my leftover 2 inside here. So anyway, any radicals are going to be simplified. What's another thing? No radicals in the denominator. That's huge. And that would be, see what we were just doing here. Rationalize the denominator. So I'll say i.e. rationalize denominators. Okay. What's a third point? A third point would be, no fractions inside a radical, which is just kind of another way of saying the same thing. No fractions inside a radical. And we saw that kind of with this example here. That's a fraction inside a radical. Well, that's basically equivalent to having a radical in your denominator. So don't leave a fraction in a radical is what I'm saying. Another thing is no negatives inside. And we had an example like that up here somewhere. Okay, like here's one of our examples where we basically... I need a good color. Brown is such a good color. We had a negative inside the cube root, so we took it out. Don't leave the negative inside. Okay. By the way, if you have a negative in a square root or a fourth root, you're going to have to stay tuned for a while to learn how to handle those. It's going to involve the number I, imaginary number type stuff. Anyway, don't leave a negative inside a radical. And what would be another one? Oh, all fractions should be reduced. In other words, if there's any canceling to be done in the end, make sure you do it. All canceling should be done. All fractions should be reduced. And I'm going to put a big PS here because it occurs to me I'm kind of forgetting this myself. PS. Remember to check that even roots come out positive. That even roots have positive answers. You take an even root, it has to have a positive answer. Boy, that looks terrible, doesn't it? Positive answers. In other words, this was the basic idea. Square root of x squared is not really just x. Not necessarily, because if x is negative, it wouldn't work. So for even root radicals, you got to make sure the right side is positive. And if it isn't, put your square root radicals in there. Now, let me actually go back and double check before we end. Let me double check. So every time I took a square root, there we go. I did it here. These are numbers. You don't have to worry about numbers. It's when you've got x's, right? So here. Well, actually, and it doesn't matter for odd roots either. Odd roots can come out negative. That's fine. Odd roots can come out negative. These are all odd roots. Woohoo, here's a fourth root. I have to make sure that the answer is positive. Is the answer positive? Yeah, x to the fourth is always positive. Okay, here, I have to make sure that the answer is positive because it's an even root. Is the answer positive? Not necessarily, not if x is negative. So you got to put an absolute value somewhere. How about right on the x itself? I'm going to write, whoops. You need to have the absolute value there. Or you have to assume that x is positive. But if you know x is positive, fine. But if you don't know that for sure, you should put the absolute value there. Okay, here's an odd root. We don't have to worry about that one. Let's see. These are numbers. You don't have to worry about numbers. Here's an x. This one's got, well, it's an odd root. I don't care about odd roots. I don't care about odd roots. Here's an even root. Here's an even root. So the principal even root should be positive. Is this positive? Yeah, because look, it's x squared. That's positive. That's cool. Okay, so I only made one boo-boo. That's good. I only made one boo-boo. Of course, the big boo-boo was not remembering to check. You should remember to check because that's going to be like minus half points if you don't do that. So make sure you do that. Okay, cool. I'm going to have to make a special note about that. I think we're done. So that gets us up to speed on radicals. Now, you know, it's a big subject. Hopefully you've seen it before, and that'll make it a little easier for you to do all this. If not, you really have to just kind of take some time, quality time, an hour at a time maybe, and just push a pencil around quite a bit in order to sort of start to internalize this. Think about what's in front of your eyes, make sure it all makes sense, and if you do that enough times, it'll all sink in. You'll be good. We'll be using these the rest of the course, so you might as well start getting used to them now.